Hello, everyone. Welcome to this exciting edition of Pivot. This session is called In Pursuit of the Holy Grail, Deep and Superhot Geothermal. My name is Steinar Jonsson. I'm the Legal and Policy Advisor for Georg, an international geothermal research cluster based in Iceland. We have an exciting team of panelists here joining us today. And I would like to invite them to introduce themselves and tell us a bit about their affiliation and background and what they are doing in the geothermal sphere. So I would like to start with you, Mark. Welcome.
Thanks very much. Thanks for having me. My name is Dr. Mark Island. I'm a lecturer in geoenergy at Newcastle University in the UK. My background is oil and gas. I spent quite a while working in the upstream oil and gas industry, exploring for hydrocarbon resources, and then a few years ago started to transfer those skills and moved over to academia to pursue research in geothermal. A lot of my current interests focus around geodynamic modeling and heat flow in the subsurface, and that's where my interests in super hot and super deep geothermal come in. I'm interested in understanding what controls the temperature distribution at depth. I'm also interested in the geomechanical behavior of those rocks and understanding the brittle ductile transition zone, exactly where it occurs, and what the implications are for the different mechanical properties of depth. So those are some of my crossover research areas.
Very good. And you, Gioia?
Hi, thanks. I'm Gioia Falcone, ranking chair of energy engineering at the University of Glasgow in Scotland, UK, where I'm also the associate director of the Centre for Sustainable Solutions. Like Mark, I also have a background in the oil and gas industry as a petroleum engineer, but then I transitioned into geoenergy applications and more specifically geothermal energy engineering problems. I'm particularly interested in unconventional solutions, unconventional designs for exploiting some of the unconventional resources. And so I look forward to this session today. Thank you.
Fantastic. Susan, if you would.
Yeah, I'm Susan Petty. I'm the Chief Technology Officer for Circ Energy. I'm also the founder and President and Chief Technology Officer for Alterock Energy, so I wear two hats. I've been in the geothermal industry for 43 years, and I've worked pretty much around the world in all aspects of geothermal energy. And currently, Alterock is pursuing research into very, very high temperature geothermal. Circ Energy is an owner and operator of geothermal power plants, and our interest is in making a product that is more acceptable and interesting to our customers who are utilities buying electricity. And so we are looking at Superhot, we are looking at thermal energy storage combined with geothermal to make a more flexible generating product.
Interesting. And to you, Karsten, welcome.
Thank you. I'm Karsten Sørli and working in Equinor in Equinor's R&D unit. Currently project leader for some of the technology initiatives we're running there, and one of them is on geothermal energy. I'm close to 25 years of track record in Statoil and Equinor, mainly working in the, of course, our oil and gas part of the business, but for the last 5 years on the renewable side with geothermal energy. And I have a background in chemical engineering. It's sort of process research has been my jack of trades with technical economical evaluation and early phase project development and evaluation of technologies. The research we are doing now in Equinor is very much founded on how to actually explore a technology position where we could make benefit of who we are and what we believe is needed in technology development to make geothermal energy an attractive opportunity for the future energy transition that we are going through. So I'm very much looking forward to today, and also bring to the table some of the experiences we have working on R&D within the Superhot geothermal area.
Fantastic. Thank you, Carsten. Well, this is obviously quite an impressive group of people here. And I think that before we go any further, I think we need to talk a bit about the terminology and the definitions. Now, how is deep and superhot defined in your view? And what exactly do we mean when using these terms? Maybe Carsten, if you would continue a bit on that.
Yes, I can do that, because we have been talking a lot about supercritical geothermal, and I think when we talk about, at least from our side, when we talk about superhot, we're not so much focusing on we're focusing on harnessing resources at supercritical conditions, but more important than being above the critical pressure and temperature is to actually look at the enthalpy that you have in your conditions, because the whole thing that we say about superhot compared to supercritical is that you're actually able to harness a resource and expand it through your well up to the surface without the phase change or transitioning directly into a superheated steam. And this is what we believe is the attractive concept here, and that is what we call superhot. So superhot is some kind of in our view, a subset of the supercritical that we are talking about.
Okay. Susan, would you have anything to add to that?
Yeah, I think with added to that is that in order to get to those very high temperatures, we are going to need sometimes to drill very deep if we want to do this in more places than in areas near volcanoes where we have very high temperatures close to the surface. So we're looking at a subset of the very high temperature geothermal also that is most likely not going to have a natural circulating conventional hydrothermal system at supercritical temperatures. So we're looking at extracting heat from very hot rock for a lot of this.
Joya or Mark? I think it's an important differentiation to make between super hot and supercritical, not to muddle and lump the two together. It's interesting that, you know, to date, a lot of the supercritical locations that have been identified are essentially below an existing high enthalpy resource, and actually understanding the mechanism that creates that heat transfer and causes that temperature rise to supercritical is key, because a lot of the research suggests that that hot water is warmed by something from below. So I think, you know, you can't untangle the two. There isn't this boundary that exists between hot and critical. You know, it's a transition. And I think what a key part I hope we'll get to is, you know, how do we explore and what mechanisms do we have to differentiate where those different resource boundaries might be? Yeah. And where globally is this most relevant? Where are these resources located primarily? Well, I think Susan touched on me, the volcanic area.
So, I mean, obviously, if we're talking about, go ahead. Sorry, Mark. I was just going to say it's the volcanic areas we know of at the moment. Those are the easy wins. You know, if you're going to use some buzzwords, those are the low-hanging fruits. You know, you've got a high enthalpy system. You know that likely beneath that it wouldn't be too much of a stretch to come up with a plausible model that would have a supercritical or a super hot resource beneath it. But actually, you know, there's other options out there, and actually maybe perhaps some of the granitic systems of the world, as we start to understand the mechanical behavior of those granitic bodies, perhaps they offer a super hot resource. I think it's important to understand it obviously will get hot with depth, but that doesn't make it a resource, because you've got to be able to abstract that resource. And I think that's, you know, where some of our understanding needs to go.
Yeah. I would begin to maybe talk about also exergy. So rather than just temperature and enthalpy, at the end of the day, as an engineer, I'm really interested in what we can convert into useful work. And so there was another parallel session that took place, I think, yesterday, where this was partially discussed as well. So rather than classifying the subsurface as something that is there in nature but may never be translated into usable by us, then we should really be focusing on the process. And as Susan hinted, I think at the end of the day, it's the flux that will be bringing some energy to us, and we want to look at the useful portion of that quantity that can be used by humanity. Otherwise, it's an interesting game, but it won't give us new energy, new sustainable energy. And so,
Exactly.
and you also mentioned standard the depth. Well, I think that's an easy one. It's deep because if you use common thresholds, it's say anything deeper than 300 or 400 or 500 meters, I think they're there. But then how deep is deep per each of the different national currencies that Mark and Susan have already mentioned, that will vary geographically. We know the countries of Italy, Iceland, New Zealand, and Japan as having been identified already for supercritical resources, but then there will be nuances around that possibly.
Right. And if we were to tap these resources globally, those that are maybe low hanging, what numbers are we talking about here?
So,
Right?
as Joya said, the available energy is really vast. And the real issue is, can we extract that heat and do useful work with it? So we're looking at truly enormous numbers. But just to give you an idea, we're working on a project with Alterock at Newbury Volcano. Now, there is no naturally occurring hydrothermal resource there. And we have drilled into the very high temperature rock, which is over 350 C. And so we're close to getting to very, very high temperatures within a short distance. Our wells are about 3,500 meters deep. But what allows us to then extract that heat is something that we haven't done yet. And that is actually create a reservoir in that rock. So it's a resource, but we don't know how to get it out yet. And I think that is what many of us are working on. And we'd use water from the surface to extract that resource. But the big benefit of doing this, of going to these deep depths, is that you are going to get something really worthwhile. So then you begin to move away from areas like these volcanoes, and then you're talking about going to depths greater than 10 kilometers or more. And then we begin to need to improve our drilling technology to be able to do that.
Mm-hmm. Speaking of drilling technology, is there some kind of a technological breakthrough that is needed to make all this happen, or is the technology already there? Karsten, I can see you're pondering this question.
I am, and I think there will be a combination of actually on focusing on drilling efficiency with the available technology, and also bringing forth new technology that can make this happen in a more cost-efficient manner. But I think it needs to be a combination of focusing on the efficiency and the competence on the drilling crews and the rigs, and applying new technology. But I don't think it's one or the other.
Right. I think we're close. I think that in these shallower systems, I think we're very close to being able to get to them and make fractures, or people are discussing other methods of extracting the heat, but doing that, and then that can help us translate to areas where we have to go a lot deeper to get these very high temperatures.
And I think it's when we say drilling, we have to be careful about not excluding the rest that goes with drilling, as in also completions and the materials that go with the process, and maybe also the electronics that go with the process. And so there are multiple challenges in one. It's not just about getting down there. And one issue, for example, with the IDDP well, the first one was the sustainability of the flow. So even if you then get to go to the depth safely, even if you manage to put the tubulars down there, and even if you manage to find some cements that can stay in place for long enough, can you then say this well will maintain well integrity for 10, 20 years. So drilling, for me, drilling is the whole picture of it. It's not just getting to depth. I mean, we've got a couple of very deep boreholes in the well. We know that magma has already been hit in several countries. So it's more about, again, converting all of that into a sustainable project. Until we do that, we don't have a resource. We have a natural energy source, but we don't have a geothermal resource.
And I guess you've got ahead of that drilling, you've got that reliability of your predictions that you'll need to make ahead. Because to put those plans to kind of access that resource, it helps if you've got a reliable method to model and predict the subsurface in the first place. And we haven't got that many calibration points once we get into these very deep systems. You know, tens of data points around the world into these very super hot systems. And so, you know, calibrating ahead of drilling is a challenge.
And on the engineering side, we've been doing some simulations of the closed wellbore solution, the deep borehole heat exchanger in such environments. So as opposed to waiting until we are ready to do a large scale EGS, let's say, or ad hoc EGS, can we already in the meantime try to maybe be less ambitious with the megawatts that can come out per well, but at least limit the risks associated to having an open system and just going in with the classic, say, YouTube or other smart downhole heat exchangers and try to recover. And we went into the settings of the Newberry volcano that Susan mentioned, for example, and we tried to do that modeling, and we got something in the range of 1.5 megawatts, depending on completions, depending on materials. And so, Stanley, you were asking for some numbers. That is one number, a theoretical number I can give you, assuming a process which is, in a way, available in much easier geological settings, and tries to be a compromise until when we are able to unlock all the technical issues with the EGS approach.
So you mentioned the IDDP project. What can we maybe set the scene a bit for our viewers? What are the deep and super hot geothermal projects ongoing in the world?
Yes, so I know there's a large audience, so I don't want to take over too much. So on the IDDP, 2 boreholes have already been drilled, and the IDDP 1 and the 2 were not targeting exactly the same location. The IDDP 1 hit magma initially, then there was a sidetrack, and the supercritical conditions were proven. And likewise with the IDDP 2, which is now currently dormant. It was ended in 2017, if I remember correctly. So we've got a dormant dragon that is ready to give, but we wouldn't probably know straight away how to manage that energy. And I'm going to let my panelists maybe expand on other sites that they may work on as well.
And IDDP, of course, standing for Iceland Deep Drilling Project.
Oh, yes.
Yeah. Karsten, would you care to weigh in here? You were heavily involved in that project.
I guess we're exploring a little bit the what's going on around the world on within this area, and I think Susan has already mentioned the initiative trying to get something going on the Newberry volcano, and then you have in Japan the Beyond Brittle project there, Japanese Beyond Brittle project. And you also have the Krafla magma testbed project north on Iceland, more a research project than the way I understand it, than industrial driven. You in Georg have been closely involved in that as well. And then you have the Hades project. I'm not sure about the status, honestly. Maybe some of the other panelists can weigh in on the status of the Hades project in New Zealand.
Yeah, I believe it's Geothermal Next Generation. That's the, I think that's the newest iteration of that project.
Oh, okay. And then you, of course, have the Discramble project in Italy, that as well. Yeah. Did I forget anyone, Susan? I see you were.
Geomatch, the Mexican one. You know, the Mexican Superhot project.
Yes.
A co-creator.
I believe you attached a slide deck, Susan, to this session, actually with the slide on these opportunities around the world. And I think it's very important that these projects find a way to collaborate, because there's
absolutely,
we have to put our resources together if we want this to happen. And I just want to reemphasize why we're doing this is actually because we believe that if we can crack this code, we actually can increase our energy intensity per well by 5 to 10 times, which has a significant impact. I think we will definitely see more expensive wells than we drill today in the high enthalpy systems, but hopefully we will get the even higher benefit on actually increasing the energy intensity. But there are so many challenges, and I totally agree with Geo. The one thing is drilling down. The other is actually doing a completion of a well that is sustainable. And we have run a project funded by the Research Council of Norway on well design for Superhot service, and the thermomechanics are actually very critical to actually being able to heat up the well and also to sustain abnormal operation during the lifetime of the well. And we have been studying sliding concepts. That's one technology that is being developed by ISUR and also others. And that we have to rethink how we do this and understand how these systems behave, because we have to think differently also with our cementing systems. In our opinion, they have to sustain the heat, but also being able to actually make the casing to some extent slide during warm up. But we have some interesting results that are now being published out of this project.
Exactly. Thank you, Carsten.
There's some really interesting research going on in the area of materials, and particularly in cements, with self-healing cements and very high temperature stable cements. But right now we can only cement casing up to about 350 C. Beyond that, our cement systems just don't work the same way. So we, as Carsten said, we have a way to go working on it, and there's some interesting research out there, but all of those things have to come together so that we can make not just a hole in the ground, but a sustainable well that we can produce.
It's probably worth that. I mean, there's a couple other locations in the US, the Puna project in Hawaii that encountered close to 400-degree temperature, and they had serious challenges there, and in the Salton Sea area as well, in the Gulf of California, which I think is an interesting area to think about, because essentially it's a very, very young rift basin. So the mechanism for the ascending fluids is slightly different to some of the other volcanic plays that we see these high temperatures associated with. And that could also feed into what's the composition of the geothermal fluids that are in these systems, which obviously plays a large part in how you go and design what's at the surface and as well.
Mm-hmm. Right. Now, Carsten mentioned briefly that the Research Council of Norway was funding one of these projects. We have a great question from the audience here. How are the projects we have just mentioned being funded?
So some of them have been, for example, Horizon 2020 projects from the European side. So they've been indeed research, primarily research or research and development projects. And what's happening potentially is that for the next step, who should be providing the next amount of funding? And there are some goals. And by the way, I would also say that the problem of collaboration is that most of these goals tend to be geographically focused.
That's true.
And exception to find opportunities for example, USA partners and European partners to work together. There's an ongoing open call at the moment, which is the AeroNet Geothermica, which I think has been discussed in another session, which is one of the very few that would allow such really international partnership to happen, although maybe the size of the grant would not be enough to drill a borehole of this type. So it's a bit of a catch-22 as to how we want to fund this ongoing research and R&D activity moving forward. But the forces would be the first thing to try and do, and maybe have a program of multiple parallel sister projects, part of the same overall investigations, trying to distribute the research questions across different sites in different places to then minimize the overall risk. I know it doesn't help as a comment, a bit general.
I think it's in the right direction. I think obviously most of these projects are funded with grant money and direct government support. So, but would you think that there's any room for venture capital, for instance, in these kind of projects, or are these primarily government funded projects?
So I can speak to that because I started Alterock with venture capital. I think that was, one of the very first geothermal companies to be funded with venture capital. And our investors at Alterock still have interest in going to these super high temperatures using EGS to avoid some of the issues around circulating hydrothermal systems that are supercritical in their fluid chemistry and stuff. So the venture capital interest is high right now, but I see another interesting development, and that is service companies and oil and gas companies who want to diversify and get more into sustainable energy production are going to take an interest in investing in some of this research and development particularly. So we've just, for instance, Alterock has just finished doing some modeling studies for looking at the resource and fracturing and development of a fractured resource system at the Newberry volcano with Baker Hughes. And their experience with numerical modeling in oil and gas and in geothermal has been a big contributor to what we're doing with them and coming up with some really interesting results. We're also working with the University of Oklahoma. And none of this is done with government grants at this point, but we definitely need that. I don't think these projects are going to be expensive, and venture capital is not going to want to take on all that risk on its own.
And the drilling, I guess, and the exploration drilling is the end goal of many of these big backed grant programs. But there's smaller steps in between which are much more achievable and perhaps can be location specific and build on the existing sites that we have around the world. You could think about geophysical methods as one of those. You could go to an existing location where we have a deep hot super well, and we can go and try a number of new geophysical techniques that are a fraction of the costs of drilling. And those learnings are not site specific at that point. Those learnings are transferable to the next time you want to try and define the next location of your super hot test site.
Exactly. Karsten, do you have anything to add?
And also, if I may add in, there are different ways of thinking of actually attacking this and actually also harnessing the deeper very hot resources. And you could actually think about drilling down and using an injection well if there's a contact between the lower parts and an upper part of a hydrothermal reservoir. And then know that OR Reykjavik Energy in Iceland are thinking about this, and that means that you could focus on the drilling and setting the well, but of course you haven't solved the issue of producing this extremely expensive or hot and possibly aggressive geofluids. But we have to take it one step at a time and trying to de-risk this in a proper manner, I think.
Mm-hmm. Right. We have linked to this. We have a question from the audience. Are drilling fluids going to become a limiting problem for super deep, super hot wells? Karsten.
There's enough Go ahead.
I'll leave it to Susan to first go ahead. Go ahead, Susan.
So at this point, we drill many of our geothermal wells are drilled with air. And we do that because we can't get drilling fluids that are stable at these very high temperatures and without, causing serious formation damage if we have natural fractures or permeability. So we largely either drill with air or water, and we then use sweeps of some polymer to get the cuttings out. But I see coming down the pike a number of really high potential energy drilling methods, and I think the next sessions will address some of that. And those methods are, I think, very interesting for Superhot because they're not going to be dependent on, a drilling fluid. They're going to use energy to make the hole. So we'll have to see how that works out and what that technology can get us. But I think there is really great potential in that area.
But I think to add to that, Susan, I think it's also important to note that the drill string and the drilling equipment and the drilling fluid doesn't necessarily see the formation temperature. What we experienced in IDDP2 was actually a fairly cold well due to drilling the last 2 kilometers with lost circulation, and the well was actually quite cold during the whole drilling operation. So it's not that you're going to have the formation temperature in the well during the drilling operation. The question is, it will be higher, but then again, when you do the completion, install the casing and do your cementing job, and then you have the warm up of actually the well, that's going to be, you have to know what you're doing. Otherwise you will experience what happened in IDDP1, where the casing actually snapped off in several locations.
And we're operating, CERC is operating a project in the Salton Sea area that's very, very high temperature. And really thermal cycling is one of the biggest issues that we have for drilling. Drilling the well, Carson's right, it stays pretty cool. The thermal conductivity of rock is not wonderful. And so when we cool off the near well bore with, whatever we're circulating air, water through there, that cooling, that heat from outside of that can't get back into the well quickly unless there's permeability to carry actual hot fluids into the well. So we end up with, in many of these circumstances, with a very low temperature well bore that then is going to heat up and subject our casing to a very big temperature differential, starting at the bottom. And then that's what the well design has to really accommodate, is that thermal cycling.
And I think that the cycling is very important, Susan, because there's been research already published that demonstrates that in less harsh conditions, even just 10 thermal cycles, say for an EOR, conventional and gas projects,
right,
lead to the loss of integrity of the completions. And so if you're talking about wells that will have to be regularly controlled by some form of cooling, even though just intermittent cooling, then how many such cycles can you do? And if you plan to have the well operational for, say, 20 years, then unfortunately your number of allowed thermal cycles will quickly be used. And so, yes, I like that point that Susan made very much.
Yeah,
Okay.
and with the wells in the Salton Sea, which are very hot, we try and minimize the thermal cycling, but we also have to select materials and connections, casing connections, that will survive the thermal cycling experience without failing it. That's a tough deal. On the other hand, I think that problem is moving towards being solved, but then you've got to solve the problem of how do you cement that casing in place? Because if you've got things moving inside a rigid cement system, then you have that's going to fail. and you're going to have to deal with that. And so one of the things that's coming along is research into self-healing cements that will actually recrystallize and heal up fractures that form during that thermal cycling. So, and that can help support our casing for a longer and more number of thermal cycles. But the other thing we need to think about is that expansion is not just vertical, so we don't just need to have things move in a vertical direction, but it also expands outward. And for that, we need to be looking at cementing systems that are more elastic and can then tolerate that horizontal expansion and also not fail, not crack. So for that, we're looking at, foamed cements that have some elasticity and other materials and other types of cements.
Exactly. We've been talking a bit about cement the past few minutes. We have a question from the audience. How important is pipe metallurgy and what is the innovation needed there?
Sorry, didn't catch that. What was it? Sorry, I didn't hear the question very well.
The question is, how important is pipe metallurgy and what is the innovation needed there? So we've been talking a bit about cement. If we would move on to all the other things we need for this to work.
So one of the things that we run into is that in natural hydrothermal systems, the fluids can be very corrosive, very aggressive, and they can also form scale really aggressively as well. We don't know what's going to happen when we do an artificially created an EGS reservoir. We're going to put fluid from the surface, which is, doesn't have a lot of dissolved minerals in it. What's going to happen to it as it flows through the rock? Will it become like the hydrothermal systems that are above the supercritical temperature and be aggressive and problematic? Regardless, our casing has to go through numbers of thermal cycles, and a lot of times the temperature of the rock that we're dealing with and the fluids that are flowing through it are going to put it beyond the heal point. So we then have the choice: do we go to a stronger metallurgy? And if we do that, are we going to run into work hardening issues and stress corrosion cracking issues that come with the thermal cycling? Or are we going to have our connections fail because of, going beyond the healed strength of the material? So we have to weigh and balance designing the well for going beyond the healed strength of the material, or we have to start looking at non-metal materials for this type of casing. And I think that's an area of research that we really need to start thinking about.
Yeah, composite materials have started to be looked at as well. And as Susan nicely put it, you have to look at all the aspects of what the casing is meant to do at once. It's difficult to isolate the mechanical integrity from the resistance to corrosion. These are also systems that we don't know how they will evolve over time when we start to abstract the heat alone and or with the fluid. And because, as Mark also stressed, some of them may be still quite young, still in evolution, are we triggering some fluid changes over time? And are we ready to say we've got casing strings that will be there in that same position and don't need to follow some movements, especially in the ductile to brittle transition? So it's a little bit like when we have to do wells in areas which are naturally seismic, where you have natural earthquakes. And in a country that has that problem, for example, we've done really some wells in my own region where one of the main challenge was how to get to prove that you can do completions that can withstand an earthquake, or if there is an earthquake, how do you ensure that the shearing is such that doesn't then lead to an uncontrolled leak of fluids? So for me, it's the full picture together, and the materials have to be justified with all these jobs that we ask the tubulars to do.
And you can couple to that if you think about we've mentioned EGS type superhot. The idea of dynamic stress perturbations as you inject a fluid or produce a fluid. At the moment, we struggle to come up with reliable and predictable models for those stress perturbations at shallow kind of oil and gas reservoir depths. I mean, we're getting better, but as we go to increasingly higher temperatures and into areas that are tectonically active, the number of variables in that model to understand how the dynamic stress perturbations impact, for instance, seismicity, it becomes a whole nother level of complexity.
Exactly.
But if I may just add to the question on piping materials, and I think that's really a key to success here. You have to withstand the thermomechanical behavior that you need, and also the corrosion. But I think it starts also with understanding what kind of conditions do you expect to experience, so you can have your design criteria right. And then what we saw in the project I mentioned with the Research Council of Norway, actually called Hot Case, was that you might find materials that can withstand this, but then it also boils down to a cost element here. Right. That if the wells get too expensive, you can't make a business out of this, and then we want to make a business here. So it's a balance between understanding the behavior you have to design for, and of course doing it with a cost that's acceptable to making a business.
What would be an acceptable cost to the Research Council of Norway?
Sorry?
Well, what would be an acceptable cost to the Research Council of Norway
I think
for one of these wells?
What we looked at then was actually doing the LCOE for the project, and trying to make a sort of an early phase design project, and see, do you actually compare to the high, if you're just comparing the economics to a high enthalpy resource, how would you actually be able to see a benefit? And if all your benefit on energy intensity is taken away by increased cost, you have to have different incentives for pursuing this path. Then it must be on a resource aspect, adding to your resource or whatever. But so we have looked for in the project we have been involved in how can we actually get a lower energy cost by having these kind of wells. And it means that you have to carefully look at I can't give you a straight answer, but it's a part of the picture.
Yeah. Very good.
Alterac has been doing a fair amount of modeling of the cost of these systems versus the energy output, and looking at possible LCOEs, given that we can get the technology to be there to be able to do it. We just assume that we can get this to work as far as the technology is concerned. What kind of reservoir do we need to have to sustain long-term production from these wells, and what kind of materials and things like that? We think that we're close, so we figure that we'll figure it out. And when we do that modeling, we get to, at a place like Newberry, where you only have to go to, say, 5 kilometers to get to temperatures of around 500 C, then in that kind of location, we could get to cost LCOEs of $45 a megawatt hour or less. And then obviously the less comes with further technology improvement. So we think that that a big piece of that cost lowering is not just the extra enthalpy, but the conversion efficiency at the higher temperatures and pressures of these supercritical fluids above the supercritical point, so that we can get, for normal efficiencies that we have in temperatures from 150 C to 175 C, we're looking at efficiencies in the 15 kind of range. Above those temperatures, we can get up to 20%. But if we go above 400 C to say 450 C, and we can get efficiencies that are over 42%. And that really begins to make a difference. So add that to the fact that you've got a higher energy density, your well cost becomes, it's always important, but it's less important because we're getting that really large amount of energy out of each well.
Okay.
I think in terms of
Interesting point.
costing, framing the costing, I think depending on the exploitation method, say if we go back to the possibility of doing these deep closed loop wells, for example, you can almost regard the surrounding environment as an infinite heat source vis-a-vis the lifetime of a well. So it could be possible to also look at the location as something that would be running for years and years and years and can rejuvenate itself over the years. So even though one well may still have a limited lifetime, you can treat it as a geothermal farm, and you can imagine a succession of wells that replace the previous, and you can actually maintain the output. So it's a different price that you have. It might be a different investment, but likewise, you do have a potentially greater price, a greater reward out of that given location.
Yeah, some of our modeling has shown that's exactly right, Joya. Some of our modeling has shown that if we can get the wells to last more than 6 years, even though they're very expensive, because our value of our energy is so high, and we've got such a high energy density for these very hot wells, that's still economic to be replacing them, say, every 6 to 10 years. Now, obviously, we would like it better if they would last longer, and I think the technology will get there. But even so, it looks to me like a solvable engineering problem to get a well to last 6 years.
Exactly. Now, Mark, you mentioned induced seismicity earlier. I was wondering if all of you could maybe tell us a little bit about your thoughts on the risks involved in that and deep geothermal, starting with you, Susan.
Sure. So when we look at going to these great depths, if we get high temperatures, if we can get to the point where we're moving into the brittle ductile transition zone, then our rock becomes plastic and less likely to fail in ways that create earthquakes. Obviously, as we cool it off, it gets brittle again. But the big thing that can result in induced seismicity that is of concern to people is the existence of large-scale faulting. And then through our efforts on the creation of a reservoir, the operation of the reservoir, we change the stress regime such that those faults slip and move. You have to have a big fault to have a big earthquake. And when we look at natural seismicity, there is a depth, temperature area where we get below that, and we don't have seismicity anymore. And we, in fact, use that information to begin to map magma bodies. We know where magma body is at Newberry volcano and some of the other volcanoes in the Cascades because of monitoring seismicity and looking for that aseismic zone. Now, the thing is that rock, is very, very hot. So what is going to happen between that brittle ductile transition zone and where we're going to start out drilling these wells where the rock is like 450 C? What kinds of risks do we have there? And the modeling of those stresses is very, very important, not just for understanding, earthquake safety and the potential for induced seismicity, but also for creating our reservoirs. So we'll have to figure these things out. Mm-hmm. And I think we're moving our models in that direction. It's one of the big areas where we can make some technology improvement.
Okay. Mark, would you like to jump in?
Yeah, I mean, I agree with lots of that. I think there's once we get to the kind of brittle ductile transition, that's true that, you know, the deformation mechanisms are different. I think when we're getting to, we've talked at the beginning about super hot, and at that point we might not be in that zone, and we could still be very much in a brittle environment, like Susan pointed out. I guess my perspective on size of fault that creates felt seismicity is a bit different. The experience from unconventional gas around the world is that many of those faults that create felt seismicity are not the large faults. They're the smaller faults that you don't know about. But you know, there's such a range of interpretations of the data, and I think one of the things is that a lot of our understanding from induced seismicity is currently from unconventional gas, and it's not exactly transferable. The methods we use to monitor and some of the tools we use transferable, but the mechanical behavior of the rocks themselves is very different. And here in Newcastle, we've been doing some work on micromechanical properties of individual minerals. So trying to kind of break the problem down into kind of the constituent parts of different rocks and how each one deformed under high temperatures, to try and unravel that complexity somewhat, because just saying, well, we can lift everything over is not quite the same. I think the re-injection issue becomes one of the key things. Is if you're thinking about an EGS system, where would you be re-injecting that cooler water? Because you might not be re-injecting the cooler water into the supercritical or the super hot zone. You might want to inject it shallower, and at that point, any cooling near the wellbore causes some thermomechanical contraction, and you know, you've got to model the whole system. My advance would be, you know, coupled modeling can't be in isolation anymore.
Jaya?
Yes, I think it's important to differentiate between induced seismicity during drilling operations, during the implementation of the boreholes and of the connection between boreholes, if we're talking about the EGS approach, versus the seismicity that could be induced during production mode. And again, coming back to potential different designs and ways of getting into those sources, maybe some risks can be eliminated or significantly reduced if taking a closed borehole approach. So I think that in the communication with the public and in the technical approach to understanding exactly the risks, it would be really, really important to be clear as to which induced seismicity we're worried about during which moment in time. And of course, the geothermal sector is actually very familiar already with induced seismicity from the EGS projects. And there's probably no need to mention the unfortunate event in South Korea at Pohang and others. So even the geothermal sector is well aware of the need for establishing and implementing induced seismicity prevention protocols, maybe systems of gates and alarms and flags. So I think this is just to say, yes, induced seismicity will have to be part of the conversation and will have to be tackled quite seriously with a transparent way of communicating when you're in the workflow of drilling, producing, injection, are we worrying about.
An adequate upfront characterization of the site can go a long way to mitigate any risk. If you've done a good job describing what you think it relates to the prediction of the right drilling materials as well. But if you can make a good, reliable prediction up front of that site, then you can plan accordingly.
But we still will need to gather some learning, so we can only speculate about what we will find down there. We will only speculate about behavior once we are in there. But at the moment, I think it's about getting to still some more pilots and learnings of case studies, and then extracting statistics from those. Otherwise, it's a bit, I think, a speculation level. It might be positive speculation, wanting to be proactive, but I do agree with you, Mark, that more surface investigations can help reduce the envelope of surprises. But still, I think for these particular types of resources, we're talking a lot about I mean, you can count the cases on the fingertips, which means we just don't have enough to draw analog learnings. And you say, my new site will be exactly as that site. And I can say that because we've drilled already 20, 30 of those. So we're still really in the learning curve, I think.
Exactly. Speaking of speculation, because time has really flown and we only have about 5 minutes left. I was wondering if you could maybe tell me, where do you see Superhot and deep geothermal in 5 years' time? Just a few words. What are your hopes and aspirations?
So I can start. I'm hoping that we'll be able to get something, actually a demonstration project with circulation at Newberry. I think that would go a long way to helping us move this forward. And once we get a circulating system, then putting power generation equipment on it is not that difficult, because that technology does exist.
Very good. Joya?
Yeah, I was saying, obviously, we see as a sector as producing lots and lots of gigawatts tomorrow. So I think time is important here. The world has the clock ticking. 2050 is a common target for many countries, and we're already in 2021. So obviously the concern is, how do we get this type of research, investigations, and pilots really accelerating? Because we know that even just a normal geothermal project might take 7 years from when you sniff the opportunity to when you actually get production going. And we're probably even behind with this type of exploratory resources and basins. So we do need to really direct the investments and direct the efforts and the resources into convergence so that we can produce them and at scale, not just as one-off projects, but at scale. Otherwise, it will remain nice pieces of jewelry as individual projects, but we won't get to 2050 net zero in a sustainable way.
Absolutely correct.
For me, on the kind of geological characterization, open access to the data and models that are underpinning these pilot projects or these demonstrator projects is key. So we can, essentially open the lid on the box and explore all those different parameter spaces and compare and contrast how we're making the characterization of the potential resource. And the more we're able to share that, the better our decision making about the next project that will get funded in 5 years' time will be.
Yeah, I couldn't agree more. Like Karsten said earlier, these projects, they have to collaborate. Karsten, would you like to say a few words?
I would definitely like to say a few words. You asked the question, where do you think we are in 5 years' time? And I think, to be honest, I think we will be still at the research and development stage, and hopefully we will be moving into demonstration. But what I really would have liked to see is that we have been able to de-risk some of the key issues relating to make this a success, and also having drilled, let's say, 2 to 3 wells worldwide. I think even 2 to 3 wells worldwide, it's an ambitious target within 5 years' time, giving the planning and also the uncertainty on the technology, some of the technology elements today. And I would definitely also like to see that we are in a more international collaborative environment where we're sharing and possibly also sharing some bits and pieces on this de-risking different technology elements to drive this forward. But I really would like to see a demonstration, but it's a full demonstration, but it is going to be tough. It's a risky, this is a high risk, high reward, hopefully, initiative, and which would possibly add to the cost efficiency of future geothermal, but also add to the available resources for geothermal being a part of the future energy transition. So, yeah.
These are all very nice pictures of the future. I think we should end it at that, and I thank you all very much for this very informative session. I have learned a lot myself, and I hope our viewers did as well. So thank you all and take care.
Thank you.
Thank you very much. Thank you.
Thanks.
Bye-bye.